Hello, everyone. Welcome to today's webinar. I am Jennifer Nyman with Geosyntech Consultants in Oakland, California, and I will be facilitating today's webinar. Today's webinar focuses on DoD-funded research efforts to minimize response time to system leaks and maximize system data to predict water use at military facilities. First, Mr. Hunter Klein will present a demonstration of an artificial intelligence leak detection technology for continuous monitoring of drinking water systems. Second, Mr. Scott Holdsworth and Dr. Connor Llewellyn will discuss their research on utilizing metering systems to predict water use. Each presentation will be followed by a brief question and answer session, and we will conclude today's webinar with a longer Q&A session. The next two slides provide instructions on optimizing the webinar. If you have not done so already, you can download Zoom with the link shown here. And if you cannot download Zoom, you may view the slides using an internet browser like Firefox, IE, or Edge, and with creating a free Zoom account. If you aren't able to view the slides or if your screen freezes, you can always try keying Control with F5 to perform a hard refresh. If you have continued technical difficulties, you can download a PDF of today's slides from the webinar webpage and call into the conference line given to you in your webinar registration email. We will also be live streaming the webinar on the CertUp and ESTCP YouTube channel at the link shown here. Today's broadcast will be listen only. You may submit questions by using the Q&A box on the Zoom screen. You don't have to wait until that Q&A period to submit your questions. In fact, we encourage you to submit questions in advance of that session. When you submit a question, please add your organizational name at the end of your question so that we can identify you. Please don't submit questions in the chat box. That's reserved for comments related to technical difficulties. And with that, I would like to introduce Mr. Timothy Tatro, who is the ESTCP Program Manager for Installation Energy and Water. Before joining CertUp and ESTCP, Tim worked at the National Renewable Energy Lab, where he focused on energy efficiency and renewable energy project development for the federal sector. Tim, please proceed.
Thank you, Jennifer, and welcome everybody to today's CertUp ESTCP webinar. I'm going to go through a few slides that give an overview of the two programs and then hand it back to get into our presentations. CertUp and ESTCP are the Department of Defense's investments in environmental and installation energy science and technology. The programs report to the Deputy Assistant Secretary of Defense for Energy Resilience and Optimization, headquartered at the Pentagon. CertUp is the Strategic Environmental Research and Development Program established by Congress as a partnership between DoD, Department of Energy, and EPA. CertUp addresses high priority environmental science and technology opportunities that focus on the top priority DoD requirements. CertUp funds both fundamental research as well as advanced technology development that ultimately impact real world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate and validate innovative environmental and installation energy technologies. These investments capitalize on past investments under CertUp or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. Advances in science and technology provide the department with the tools needed to effectively manage and restore its assets to protect troops, their families, the public, and the environment. CertUp and ESTCP investments improve installation energy resilience, environmental cleanup, UXO remediation, resource conservation, and the sustainment and maintenance of defense assets. CertUp and ESTCP fund, monitor, and actively guide relevant and applied research, development, testing, and evaluation projects for the DoD's top environment and installation energy challenges. Our programs currently fund over 600 active projects. To maximize research impact, CertUp and ESTCP collaborate with top talent across sectors. In 2023, we funded projects with 77 academic institutions, 91 federal performers, 52 industry partners. Our innovation and technology development inform DoD policy and ultimately improve environmental and energy management. Our webinar series highlights outstanding projects across all our main focus areas. In the next webinar in the Installation Energy and Water program area is scheduled for June 13th. It'll be focused on microgrid implementation and considerations for improved energy resilience. Registration is open for all our webinars through the end of this year. You can find additional information about upcoming webinars at the link here, and all past webinars are archived and can be accessed using this link. I'd like to remind you that a copy of today's presentation can be downloaded from our webinar webpage. And we would appreciate if you can please take a moment to complete the survey that will pop up on your screen at the end of the webcast. So with that, I will hand it back over to Jennifer and you can introduce our first speaker.
Great. Thank you, Tim. It's now my pleasure to introduce Mr. Hunter Klein, who is a chemical engineer at the Naval Facilities Engineering and Expeditionary Warfare Center. Hunter has 4 years of experience in the field of environmental security and compliance. He has assisted and served as the PI for several research, development, test, and evaluation projects relating to energy and water resiliency efforts. These have included demonstrations involving expeditionary waste-to-energy systems, wastewater and potable water treatment systems, and advanced leak detection technologies. Hunter earned a bachelor's degree in chemical engineering from University of California, Davis, and a master's degree in material science and engineering from University of California, Los Angeles. Hunter, please go ahead.
Thank you for the kind introduction, and welcome everyone. So as was mentioned before, I'll be talking today about one of our demonstration projects regarding an artificial intelligence-based leak detection technology. So I'll begin here with a quick presentation outline, and I'll first start with some background info on the project and then go into a little bit more detail about what the technology is, as well as briefly how it works. Then I'll give some more detail on the actual demonstration project and talk about some of the testing that was done and our results and findings so far. Then I'll end with a brief overview of our conclusions from the demonstration and some of the DoD benefits. So this slide's to help give some background on why we began the project. So in general, the DoD water infrastructure is several decades old and typically much older than your typical municipal system, which makes it much more prone to leaks. And as a result, these leaks can become more severe over time and cause issues such as service disruptions, floods, sinkholes, or other forms of infrastructure damage, which makes it essential to identify and repair these leaks as early as possible. And some of the current approaches to identifying leaks is to perform these water audits or water surveys, where teams may go out with geophones or other leak detection technologies to identify leaks. But the main problem is that these surveys are infrequently performed and your water system is still vulnerable between surveys. So yeah, that's really what led to this project, where our goal was ultimately to demonstrate a fully autonomous system that allows for both continuous monitoring and leak localization, which should help teams identify and locate leaks as early as possible and better support those early mitigation and repair efforts. So moving into what the system is, at its core, it is an acoustic-based leak detection technology that primarily relies on a hydrophone to detect the noise from leaks. So looking at the image of the installed system on the right, you can see that it's mounted directly to fire hydrants, with the benefit here being that it allows the sensors, which are located in this bottom ring here, to have direct access to the water column. And this helps to reduce potential signal losses and background interference, ultimately increasing the sensitivity of those sensors. And this increased sensitivity allows the sensors to pick up leaks in both metallic and plastic pipes, where I believe a lot of the conventional approaches that may rely on placing, listening device or hydrophone on the pipe exterior, for example, start to struggle with, HDPE or PVC piping. And then the other sensors included in the sensor station, which help to improve accuracy and enable the leak localization, are an accelerometer, a pressure sensor, and thermometer. With a minor side effect or side benefit of the pressure sensor being that it also enables the detection of pressure transient events, otherwise known as water hammer, which can be another source of infrastructure damage. And then located in this external box is a USB access point to connect a laptop as needed. Then there's also a rechargeable lithium-ion battery, which we've been getting about 8 to 12 months of charge out of. And then there is also a wireless receiver and transmitter to allow transferring data over cellular networks from the sensor station to a central server where all of the data processing occurs. So this slide gives a brief overview on how the detection and localization works. So starting with the detection side, when a hydrophone picks up an increase in noise compared to the baseline, that really signals that there could be a leak nearby. And then we're also using AI and machine learning approaches to further filter out any potential background noise in order to isolate the leak as much as possible. For the localization, we're essentially extracting the signal peaks from the acoustic signal and comparing the time of arrival when the matching peak will reach each sensor station within range. And because we can calculate the speed of sound within the pipe at a given pressure and temperature, we can estimate how far from each sensor station the leak is. And then when we consider the pipe network geometry from GIS data that we import, we can use this maximum likelihood estimate to calculate the most probable routes for the acoustic noise to help locate exactly where the leak is on a pipe section. So this slide should also give some background on the previous developments that have gone into the technology. And prior to this project, most of the testing that had been performed was on dry barrel fire hydrants in Canada. And while the dry barrel hydrants are typically more common throughout colder climates where freezing is a concern, a majority of the Southwest installations, and especially those in Southern California, typically will use wet barrel hydrants. So the system had to be slightly redesigned for this demonstration to accommodate that. And I believe this actually made the installation process simpler, since the sensors didn't have to be lowered down into the pipe main and could be instead mounted directly to the hydrant. Some of the other minor design changes were to help meet the DoD requirements and specifically the cybersecurity requirements that I'll touch on a little later. And then we also plan to incorporate the more advanced AI and machine learning approaches that the University of California, Los Angeles has been developing and improving on over the last few years. So looking at the actual project objectives, the goal was to demonstrate and validate this redesigned system in a DoD environment at Naval Base Ventura County, Port Hueneme, and evaluate the sensor performance in terms of detection accuracy by looking at things like any false positives or false negatives, the localization accuracy in terms of how close to the actual leak the estimates are, as well as some more subjective measures such as the ease of use for both the sensor stations and support tools. And then also looking at the overall reliability of the system for its use case as a continuous and real-time leak monitoring technology. So as mentioned before, the system does rely on wireless data transfer to transfer the data from all the sensor stations to the server for the data processing. And with that comes much more strict DoD cybersecurity requirements, and ultimately the need for an authority to operate, or ATO, in order to implement the system. For our demonstration, we felt it would be easiest to split it into 2 phases, with the first phase being to test the system without any wireless capability, and instead manually download the data to a laptop in order to simplify these cyber requirements and allow us to begin the baselining, tuning, and initial validation testing while we simultaneously work towards the more involved approvals needed for the second phase. And then we've also been working with our local cybersecurity team to put together a risk management framework package, which should serve as a good basis for future ATO approvals and drastically cut down the overall amount of effort and time needed for procurement. So this is a map of our demonstration site at Naval Base Ventura County. And we identified this location with 5 nearby hydrants, as well as a couple alternate locations that fit most of the criteria that we needed for our testing. So first off, all of the hydrants in this area were of similar make and model, which helped to ensure system compatibility and that we could move around the sensor stations or the leak simulation setup if necessary. Also, the distribution network here had a variety of features that could be more representative of what would maybe be found in a larger or overall system. So we had a couple long straight sections with multiple hydrants. Then there's also a turn and a T-junction. So also the site is in close proximity to both NAVFAC, EXWC, and UCLA, which made a lot of the hands-on work, and especially the hands-on work for the data downloads in phase 1, much more feasible. So this slide shows an overview on how we approach that first phase. So the first step was to baseline our system for about a month or so without any known leaks in order to get an idea of what the ambient noise levels are at various times throughout the day. And this helps with setting the basis for the AI and machine learning, the noise filtering, and detection methods. Then after the baselining, we started some of the actual validation testing, where we would perform our leak simulations at known locations, and then physically go out to the demonstration site every couple of weeks to download the data to a laptop, and then subsequently transfer that over to the server for processing. For our leak simulation testing, we essentially connected these automated sprinkler timers to either a hydrant, like the left image, or a fire suppression valve, like on the right. In the right setup with the fire suppression was maybe a little more realistic in that it's not placed directly on top of a sensor station. However, we were limited with this valve to a flow rate of only 10 gallons per minute. So for any of the higher flow rate testing, we had to use the hydrant setup. And so what we would do is set the leak to begin in the middle of the night to help minimize any potential background noise like traffic, construction, or pumps. And then we would set the sensor collection period to record a little bit before and then end a little bit after the leak so that we could easily observe the change in acoustic profile throughout the leak simulation. And while performing this late at night is really an idealized case, it's not too far off what a real implementation could look like, since the collection period realistically only needs to be run for about an hour or so, either once or twice a day, to effectively get continuous monitoring while also maximizing the battery life of the sensors. And then if you want more or less coverage, you can configure how often to collect data if necessary. Then looking at the acoustic results from the leak simulation testing, you can notice that prior to the leak, all of the sensors are showing relatively low noise signals. And then as soon as the leak begins, there's a significant jump in the overall signal strength, especially with the sensors closer to the source, which in this case was a hydrant 2 or the orange dots. And this was demonstrating that the nearby sensors can effectively pick up the change in noise associated with their leak. And then as a rudimentary first pass for the localization, the relative signal strength could be a good indicator generally of where your leak is. So again, looking at the figure on the right, the relative signal strengths could show that the leak is maybe closer to hydrants 1, 2, or 3, the orange, blue, and pink dots respectively, as compared to hydrants 4 or 5. But it's worth keeping in mind that there is more uncertainty in using this. So if you notice that hydrants 1 or 3, or 1 and 3 are roughly the same distance from the simulated leak, However, hydrant 1 is showing a much stronger signal than hydrant 3 because it's more unobstructed. So that's really part of the reason why we're using the time delay rather than relative signal strengths, since it's overall more predictable and a better parameter to use for the localization. So then moving to the localization results for phase 1, generally the system is fairly accurate. And looking at the figure, you can see that most of the grouping is near the actual leak location. But one of the issues that we were finding is that over time, we were getting more and more inaccuracies due to the sensor station's onboard clocks starting to drift out of sync from one another. And this is typically a common issue with these network isolated systems. And then the clock drift also gets accelerated by temperature shifts affecting each sensor station differently. And this was significant because the localization algorithm requires a very accurate time synchronization to effectively use the time delay between signal peaks, and any small difference there can really affect your total accuracy. Some potential mitigation methods that we've thought of is to synchronize the sensors as often as possible, which is easy to do with wireless connectivity, but when doing it manually, it's typically only done when the laptop is connected for downloading data, which maybe isn't the most practical as a long-term solution. And then potentially we could also look into using more temperature resilient onboard clocks for the sensor stations, which could help improve the overall accuracy even when we add in the wireless capabilities. And that brings us to some of the other drawbacks of the isolated system, in that it effectively limits the capability to no longer be a fully continuous and real-time monitoring technology, which is why throughout this demonstration and project, we aim to pursue the full wireless implementation for phase 2, despite all of the increased cybersecurity requirements. Some of the other problems that we ran into are that it's more difficult to monitor the sensor status to identify if maybe a sensor fails, or if there's a low battery or some other configuration error, which again is something that can be alleviated by adding in the wireless communication. So with that, a potential use case for the standalone mode could maybe be for a short-term leak audit or survey where the effort to obtain that ATO doesn't really make sense, but it is worth keeping in mind some of the feasibility issues, in that you're limited by the data transfer rate, which could be anywhere from 10 minutes to hours per hydrant, depending on how long you go between downloads. And then looking at our laptop setup on the right, you can see it's not really the most ideal, and overall is a time-intensive process to continuously monitor the script and ensure that there's no errors or pauses with the download. And then also ensuring that the battery on the laptop doesn't die. Then in addition to this, there's also that issue of the increase in accuracy due to clock drift that I was mentioning on the last slide. And then this leads into the second phase of the demonstration, where we added in the wireless modules to take advantage of the full capabilities of the technology. And adding in the modules was a simple retrofit. And once installed, we essentially repeated the same leak simulation testing and validation from phase 1 to get close to a one-to-one comparison between the two setups. And some of the benefits of this are that it allows for quicker upload times, where the data is automatically uploaded to the server and the results can be viewed on the web portal about 5 minutes later. And then the sensors can be set to synchronize with the GPS clock right before the collection period to minimize that clock drift issue as much as possible, which should increase the accuracy long-term compared to phase 1. And then in terms of troubleshooting, the configuration files for all of the sensor stations can be viewed and updated remotely to adjust things like setting when or how often the data is collected. And then we can also remotely view the sensor status, and alerts like a detected leak, a pressure transient, or low battery can be set up as an email or text notification that gets sent out to end users. So looking at the localization results from phase 2, again, we get a grouping near the actual leak location. But you can see with the plot on the right that the most dense cluster of estimates is within a 50-foot radius. And the average was about 150 feet. So overall, these results, and especially the figure on the left, may look similar to what was shown for phase 1. But now we do have the added benefit that we can maintain this accuracy over time with less of an impact from clock drift. Whereas those results in phase 1 would quickly start to lose accuracy in as little as maybe hours after synchronizing all of the clocks. And this slide shows actual screenshots from that web portal that end users would have access to. So on the left are the acoustic results, similar to the figure that I showed a few slides back. However, here it's just zoomed out to show a week's worth of data. And then you could zoom into a specific section or day if you want. And then in the case of the demonstration, this demonstration, we had a constant leak noise during all the collection periods. But the idea is that if there was a real leak, you would be able to see an increase in noise over a few days, which could really help you identify if there is a leak, and maybe even approximately when that leak began. Then the figure on the right is arguably the more useful figure, which shows both the detection and localization results. So the red and orange circles are the detection overlay, and these rings will typically get larger and then change from orange to red as the system becomes more confident that there is a nearby leak, with the idea being that if you were zoomed out at a full installation level and had several sensors, it becomes easily and quickly apparent where the leak is. Then when you enable the localization overlay, you get this black ring, which highlights the radius of where the system believes the leak is. And this will typically get smaller over time. And the goal is to help cut down the search region where teams would need to look in order to repair a leak. So that brings us to some of our conclusions that we came up with throughout the demonstration. We found that the ability to implement the wireless communication in order to get the real-time monitoring, the more accurate long-term results, and the reduced hands-on operation really improved the end user experience, and overall was a more practical way to use the system, provided that you can get all of the proper cybersecurity approvals to do so. And then overall, we found that the sensor stations were effective at detecting and locating our simulated leaks, with only a handful of false positives or missed leaks throughout all of our testing. And the web portal was also easy to operate and understand with minimal training needed. As for some of the DoD benefits, this technology primarily helps to support early leak mitigation efforts, which also ties into water conservation and water savings benefits. Then other benefits are that it can help reduce the risk of property damages and cross-contamination that are often associated with severe leaks. And then the capability for email or text alerts can help improve response times and help ensure awareness to potential leaks or other critical issues. And then finally, the ability to detect pressure transients with the onboard pressure sensor can further help with distribution network resiliency and reducing your risk of infrastructure damage. And yeah, so that's all I have for you guys today. And I'd like to give a big thank you to our project team, especially those from UCLA, Digital Water Solutions, and Naval Base Ventura County for making the demonstration possible. And then also a big thanks to ESCCP and the entire webinar team for setting this up and helping to make the process as smooth as possible. And so with that, here's the ESCCP project number and information, and then also my contact info if there's any follow-up questions that we can't get to today. So thank you all for your time.
Great. Thank you, Hunter. We appreciate it. To our audience, you may now submit questions for Hunter on his presentation. Use the Q&A box on the Zoom platform to do that. We do have a number of questions for you. So first, Hunter, can you use this system to detect leaks that were existing prior to installing the system, prior to baselining?
Yeah, we believe we can. We believe throughout all of the testing we've done through this demonstration and some of the past testing that was done, in Canada, that we have enough overall data to identify a pre-existing leak. But I still believe that doing some baselining after that initial setup might still be beneficial.
Sure. Okay, great. And then you talked about needing to charge the individual stations. Have you ever thought of the concept of using small solar panels at those locations to charge batteries?
I have not, but that's a great idea I could pass along to our contractor to see how feasible that is.
Okay, great. Have you considered using distributed acoustic sensing instead of these point sensors, because that might improve detection accuracy?
That might be a question I can pass to the contractor. I'm somewhat unfamiliar with what those sensors are.
Gotcha. Okay, we can follow up, certainly.
Yeah.
Great. So you're using these sensors on hydrants. Can this approach still be used where there is a distribution system without any hydrants, or if hydrants are on a separate network for fire suppression?
Yeah, I think that ultimately is installation specific. One of the downsides of the technology is that you do require a frequent access point. So if something similar exists that we could, retrofit or attach the sensors to, that could be a possibility, but it really is installation specific in that sense.
Gotcha. Okay, thank you. We've gotten a few questions about the cybersecurity requirements that you did talk about. Can you say a little more about what the cybersecurity considerations are if you're implementing this system with online wireless data collection?
Yeah, so for the ATO, they want a lot of information on the software, the encryption and all that, as well as the hardware components. So they were primarily interested in like what the server's running, how we're getting the data across. So that's all covered in the RMF package. And then past that, there's a lot of installation specific questions towards getting cyber approvals that I'm not as much familiar with. But yeah, it is installation specific past the initial hardware and software considerations.
Okay, that's helpful. Thank you. Is there any way to estimate the leak volume or the intensity of the leak, the flow rate using this system?
I don't believe so. Maybe if you're looking at that relative signal strength, but again, it's somewhat unpredictable to know how your pipe geometry might affect the signal strength. So I think it's more tuned for just the technique of the leak rather than your volume of a leak.
Okay, gotcha. All right, and we have a couple of questions about cost. So did you determine an approximate cost per unit? And then is there an estimate of about how many linear feet of pipe that one unit can monitor?
Yeah, so each sensor station, I believe, runs about $5,000. And realistically, you need a minimum of 2 to 3. And throughout our testing, the max range from the simulated leak to the farthest sensor was about 1,200 feet. So you can maybe go a little farther than that, but I'd say, about 1,000 feet is your range.
Okay, great, very helpful. We had a question about whether there were interferences like traffic or time of day that impacted data interpretation. Or is the system set up that it could just be monitored at the time of day with the least interference?
Yeah, so we can set it up to be, that collection period at the time when there's least interference. Through our demonstration, I think there was a handful of false positives that were probably from traffic noise or something. But overall, the AI does a good job at filtering out all of that noise as much as possible.
Okay, great. Is this technology currently available in the market, or is it just being set up to be used within DoD? And if it's available, can you tell us through what company?
Yeah, so Digital Water Solutions was the primary contractor for the hardware. And they do have at least the dry barrel setup commercially available. And I believe the wet barrel setup probably also is or could be soon. And then their lead time for that, if you go through them for purchasing, is about 6 weeks, I believe.
Right, great. And have you experienced any other interferences, like from or could you imagine any other interferences? Like, what if there is pumping equipment nearby, or strong electrical sources, or significant changes in soil? Would any of those things potentially make a difference?
From those examples, I believe, the things that generate noise, like the pumping equipment, would generate the most interference. I think the soil maybe could change your leak profile, at least initially. But the system should adapt, or if the leak cuts out an air pocket, it should go back to what we've been experiencing so far. And then maybe electrical interference could impact, I don't know, your cellular signal, but I don't think it would be much of an issue there.
Okay, thank you. The next question is about the algorithms. Are those algorithms, like the AI or machine learning algorithms, being updated as the data is being collected, or do you just update it once you do the baseline? And then you can assume that it's good to go for the rest of the implementation?
I believe, I'd have to double check, but I believe it does update and kind of learn and adapt to your system as it continues to record data.
Okay. Thanks. And then I think we have maybe one final question for you, Hunter. And that is any training needed for a user, or can any manager at a DoD installation, be implementing this technology with a dashboard without a lot of training needed?
Yeah, so for at least our demonstration, our contractor gave us like a 1 to 2 hour rundown of the web portal. And after that, that was really all we needed to understand the web portal and how to use it. And then anyone doing maybe periodic maintenance on the system would need a little bit of training, but it seemed very minimal throughout our testing.
Yes, that does seem minimal. Great. Okay. Thanks, Hunter, for answering all of those questions. And for our audience, Hunter will come back on the line at the very end of the webinar. So if you have more specific questions for him, you can note that if you submit a question in the Q&A box indicated for Hunter. Thank you. And now our second presentation will be split between two speakers. The first is Mr. Scott Holdsworth. Scott serves as Headquarters U.S. Marine Corps Installations Command Facilities Energy Management Program Manager. He is responsible for establishing policy and obtaining resources to ensure that the Marine Corps implements a proactive approach to improve its energy resilience and security posture and mitigate unacceptable risks to critical energy requirements. Scott received a bachelor's degree from Dickinson College and an MBA from the University of Maryland. The second speaker today for this presentation will be Dr. Connor Llewellyn, and he is a lead water infrastructure engineer at the MITRE Corporation in McLean, Virginia. He has over 15 years of experience working in the water sector in design, research, consulting, and developing and implementing technologies. Connor is a professionally registered civil engineer who has authored numerous peer-reviewed papers. He also serves as an adjunct professor of civil engineering at Villanova University. Connor received his bachelor's degree in civil and environmental engineering from the University of Maryland and his master's and doctoral degrees in civil engineering from Villanova University. So Scott, get us started for this presentation.
All right, thank you very much. Again, my name is Scott Holdsworth. Thank you for the opportunity to speak on what I think is a very interesting topic, and it's certainly important to me as we try to obtain limited funding resources to address water management across the Marine Corps enterprise. During this presentation, I'll give a brief description of the background and the problem statement we're trying to resolve, and then Connor will break into the more interesting aspects of how, what, and where we're trying to achieve these initiatives. So walk through the examples, and then ultimately we'll wrap up with some conclusions that we have found in our project demonstration. So background, from my perspective, I need to have a knowledge of what consumption levels water is used at our installations, and I want to have an understanding of where it's used. As we look at installing meters, we recognize that meters provide data. That doesn't necessarily constitute information or knowledge. Data needs to be processed and analyzed to create information, or any proactive actions can be taken, and that the true success of our program is when we take that information and can actually create an actionable capability. When we break down meters, a big part of that is what is the cost to our overall program, and there are 5 variables that we look at. Number 1, deployment of the meter. Number 2, cybersecure communication. Number 3, data acquisition. Number 4, data analysis. Finally, number 5, how are we going to sustain those data, or how are we going to sustain those meters? Again, each of those factors contributes to the overall cost. And one of the key goals on my end is, if I can reduce the number of meters in my portfolio, that can help to reduce those costs in what is a very, very competitive funding environment. Second aspect is at the installation level. They need the analytics to better understand, again, what their consumption levels are, where they're using the data, how they can predict future consumption levels. Why is this important? Again, the second aspect of cost is not just the metering, but it's also the impact on our overall utilities budget. Having a better understanding of how water is used can contribute in identifying future projects, targeting reduction of consumption, and also important is just the general area we are looking at. This project specifically was at Marine Corps Air to Ground Combat Center 29 Palms in California. Clearly, there's been water issues, concerns about availability in that part of the country. And so, again, having that understanding of analytics so that we can make better decisions in the future is important as we move forward in terms of prioritizing funding and resources in the future. And with that, I'll turn it over to Connor, and he'll walk you through the details of the project. Thank you.
Thanks, Scott. Thanks for the great background. I'm Connor Llewellyn. I'm going to talk about the project approach here, some of the initial results that we're seeing, and some conclusions that we have so far. So this was funded starting June 2023, and we go through September 2024. So we're kind of in the midst of things. So the word conclusions, may be updated as we go along. But I think Scott, really did a good job of describing what the problem statement is. Acquisition and operational costs of metering can be limiting, not just acquiring the meters, but installing. Cyber issues, and even just having the resources to maintain and use that data. Current approaches that can utilize metering data often lack fidelity. Fidelity, I mean, we're looking at water use on an annual basis, when it's probably more helpful for especially certain facilities to look at a more granular level, whether that be monthly or daily or even finer than that. This is used for really regulatory compliance. But being able to know more about seasonal or different kinds of dependencies for water use can be really helpful when planning for future. So the big question we wanted to address and try to answer as part of this work was, how can we leverage some of these analytical models that have been leveraged in academia and even the commercial sector to better predict water use at installations. And really the goal was to try to create a hybrid metering approach. So we want to use analytics not only to predict, but also prioritize locations for additional metering, so we can really get a cost-effective, good understanding of water use at the installation level. So some of the main objectives that we're trying to address as part of this study really breaks down into five steps or tasks. So really understanding the state of the practice for existing approaches in terms of water use estimation and metering. A big portion of this is data collection to establish water use and infrastructure baseline at one installation, as Scott mentioned, is the 29 Palms installation. Utilize that data to develop analytics. And when I say analytics, I mean we're using really a wide variety of approaches, from simpler approaches like developing monthly averages to compare to actual data, to more complex approaches like machine learning and recurrent neural network approaches. Using those analytic results, integrating that into a geospatial platform to be able to develop a tool that installation operators and managers can use to interact with the data, interact with geospatial infrastructure data to get a better idea of installation and facility level water use, and then of course reporting and technology transfer. So just an overview of some existing approaches. The big one, a well-known one, is really annual water use intensity. Water use intensity is looking at, it's using meter data often to develop a water use per square footage of the facility. So this is often represented as gallons per square foot. And this is used to track annual water use reduction goals often. From that kind of more aggregate data, we can produce daily estimates based on population. So you can use base population or facility population to develop a per person per use kind of daily estimate, or process. The Department of Energy has developed different estimation methods for different processes at installations for things like car washing or irrigation. And that's where that third bullet comes into play, climate and land use approaches. So we often see climate information and land use or vegetation information included when trying to estimate annual water use for irrigation for different parts of the country, or for different land use types or vegetation types. And then another approach that is DOE provides a lot of information on our walkthrough survey. So basically going through a facility, getting an idea of the flow rates for different faucets or toilets and things like that, to get a better idea of how much water is being used at a facility, and using that for overall installation water balance modeling. A lot of those approaches, or at least the water use intensity approaches, rely on some level of metering data, even if it's a small amount. And that can be advanced metering systems, we'll call AMS or AMI meters, advanced metering infrastructure, or just manually read meters. So when I say advanced metering infrastructure, there's an example on the right there of, it's a meter that has the capability, it has a software typically associated with it, where we can view almost in real time water use, or every 15 minutes or so. And there's a database that data is collected over time. So it gives users the opportunity to get a really granular look at the water use data happening at a facility or a place where that data is being monitored or metered. Manual read data is a meter that somebody goes out and reads every so often, so monthly for this case. And these meters, especially AMI meters, can be very valuable in terms of understanding water use, specific water use at facilities at the installation level. There's a lot of commercial providers of AMI/AMS meters that have specific platforms that go along with their meters. These are often available for software as a service fee, SaaS fees, or sometimes network as a service fees. Some of the things that Scott talked about kind of ring true here in terms of difficulty to integrate, to operate, to maintain. And even when these systems are up and running, installations at times don't have the resources to really dive into the data, to do the analysis, to get more insights from that data. So, one of our goals as part of this was to use some of this existing data to try to develop some of those analytics and some of those some approaches that would allow users and installation operators to get more insights from existing data. As Scott mentioned, the facility that we're working with as part of this project is 29 Palms. Some interesting notes about the installation: they operate and maintain their potable water and wastewater systems. They have a network of both AMI meters and manually read meters. So there's good coverage throughout the installation, a lot of different facility types and uses to pull from as part of the study. Fairly long record for some of these metering locations, especially at the installation level, up to 15 years of water use. As I mentioned, a variety of facility categories. And one interesting thing was the installation is close to several other installations. So for any potential future phases of this work, the idea would be that these results in the platform could be easily scaled up in locations of similar climate. As we see, probably fairly obvious from the picture to the right there, it's a very dry environment. It's something like an average annual rainfall or precipitation of 4 inches per year. And if you can guess where the golf course is, good for you. But other similar installations with similar climate, hopefully we could be able to scale these results up. So one of the key portions of this is the data collection phase, and this is both collecting existing infrastructure data, including really focused on existing meters out there, so we can figure out how well the installation is metered and where any gaps are, and then available water use data. So you can see some examples of existing meters at the installation in the picture to the right there. This included a field visit with the installation, a review of the available geospatial data. So this is great. We got to see the different types of meters, different kinds of platforms, and different data collection platforms that are being used. As part of this, we learned that a good portion of the historic AMI metering data had been lost due to a software failure upgrade. So this reduced the number of meters that we'd actually have data from for this analysis. So we went from having something like 200 meters to work from to something like 40. So we're using manually read data from manually read meter data from the installation to develop some of these analytic methods that we'll be talking about today. And some of the other data that we collected were category codes, different facility types on the installation, climate data, which was just publicly available using NOAA data, base populations, so not just populations, but training schedule to get a better idea of when there might be an influx of people and an influx of water use at the installation. And the discussions with operations staff, this was really valuable in terms of figuring out why specific peaks or valleys are happening in water use data to better understand when looking and performing analysis on the data set. So once we perform the data collection, really utilize that historic water use data as the main input for analytical model development. And the very general high level steps we're following is in this flow chart at the bottom here. So the data collection, utilizing the historic data, data pre-processing analysis. So this is a pretty big lift in terms of taking data from disparate metering, disparate data sets, and cleaning it, formatting it in a way to make the model development portion easy. So especially when using manual meter reading data, the type of data that we're seeing is depending on who was collecting metering data that month. So there are a few different formats that we had to organize and put in the same kind of easy to use format for a model development. So that was a pretty significant lift. And as part of that was some initial analysis, just looking at time series and picking out any obvious correlations, seasonal and temperature, things like that. So really in the thick of the model development and the evaluation application phase currently, which I'll share in a couple slides here. So our initial modeling focused on installation-wide use, and this was mainly because this is the longest data set that we had and really the cleanest data set that we have. They were pretty clearly seasonal trends in water use that we were able to use for some initial model development. And we were able to, not just use the installation data set, but use the surrounding town data set. So the 29 Palms Water District publishes their monthly water use data online. So we're actually able to develop some of these methods or utilize some of these analytic methods to make sure that they're transferable to similar locations and similar climates with similar populations. So this is the first example of initial modeling that we used on the 29 Palms Water District data. So this isn't the installation, this is the surrounding town. And the method that we're utilizing here is a regression-based method. It's a autoregressive integrated moving average, or ARIMA. And we're showing a few different things on this graph. So we've got our blue data, that's our training data. So that's just the historic water use data from the water district that we're using to train that predictive model in green. The orange is the test data. So that's just a continuation of the historic data, but we're using that portion of it to test our predictive models. So one thing that jumps out to me looking at this is those peaks in historic use in 2020 and 2021. So those are actually, as part of the regression model, we're using temperature and precipitation along with the water use to train our predictive model. So those were 2 years that had higher temperatures than we had in our training data set, which caused us the model to miss those peak water use, which was really interesting. But for the remaining months where the remaining of the time series, the model performed pretty well. There was a percent error of about 8% when compared to the test training set. And that's great when you have, sort of clean data, I'll say, but, we need to have models that work with messy data, I'll say too. This is a view of, this is unitless installation-wide water use data for 29 Palms. As you can see, it follows a similar seasonal pattern. It's peaks in hot months, lower in cool months. But there's a lot more variability in terms of what that peak is, what those valleys are. So we needed models that had the ability to predict even when the data isn't as neat. So this is using a more complex approach. It's a recurring neural network approach called long short-term modeling, LSTM. And you can see, compared to the raw historic data, the blue training data, especially looking at the green predicted test data, even in periods where we have big jumps in usage, the model's still performing pretty well. So we had an average error of about 12% when compared to the historic data. And the way this model works is at a very high level. We're using that historic data as a look back period and putting specific emphasis on the previous 12 months. So data quality is obviously important. This was one of the better data sets that we have in terms of the length of it and the quality of data from the installation. So we're able to use some of these more complex models to get pretty decent results. When we look at the facility level data, we go from, clean to messy to even messier. So there's less data in some cases. So we're using a smaller data set, more variation, and less really seasonal patterns when looking at the data. So you can see the training data or historic data. There's a lot of peaks, a lot of valleys that are not easily explainable just by looking at the data. And you can see from the prediction compared to the actual test data, accuracy is not this model's strong suit. You might say that this is doing a good job of picking out data anomaly, which is probably true, but we'd certainly want to do more evaluation around what the appropriate models to use for at the facility level when we have this type of variable and kind of messier data. So one thing I want to harp on again is quality. Data quality is important. The amount of data that we have is really important when training these types of models and understanding the data and why we're seeing certain spikes, if those can be explained. So this is just showing a comparison of some of the different model approaches that we use, all the way from monthly average, so kind of just a very general average approach, to regression, the ARIMA, and the recurring neural network machine learning LSTM model. But what we're determining is really that there's, at this point with the data that we have, there's probably not a one-size-fits-all approach, and that for some of the facility level data, we'll probably develop or utilize some of these monthly average, or utilize facility-based or category-based water use intensity monthly values, with some add in some seasonal dependence there based on some of the data that we're seeing. But even though we have these complex models, without the data to actually develop those accurately, at the facility level, we haven't seen so much success so far. So we'll continue developing those and evaluating those. But really what this graph is showing is that with a good data set, that more complex models can be very valuable in terms of water use prediction, but that data is really important. So where we can't use any analytic approach to accurately develop water use, or we don't have confidence around any of those estimations, we'll prioritize those locations for additional metering. And as part of those, the analytic results, we're integrating into a geospatial tool to allow users, installation managers, water managers to interact with the prediction data, interact with historic water use data at the installation level and at the facility level. So we're utilizing the Esri Insights tool for this, and this is hosted on the Marine Corps GeoFidelis platform, which is their geospatial platform. So this tool will be CAC enabled, available to the installation managers to be able to interact with. And our goal is to, we have an initial prototype. This is actually an older picture of it. We've since updated, but gives you an idea of what the interface would look like. Our hope is to kind of give this a test run to the installation folks this month and get some feedback, really focused on kind of what they want to see, the usability of the tool, and how it can keep improving it. So the next steps, continuing the analytic approach development, focusing on the facility level estimates, apply those results to unmetered locations to get predictions of those locations, and use that data for prioritization, perform a more rigorous evaluation of these analytic modeling results, including statistical testing, continue development of the geospatial tool and fully integrating those model results, and incorporating feedback from installation staff. And the final technical report for this phase of the work is due September 2024. So conclusions, we heard Scott give a good background about why water use and understanding water use cost effectively is important for the Marine Corps. AMS, AMI metering can be very useful in tracking water use, but there are complexities that come along with this. Analytic approaches can be valuable in predicting water use, can be used to complement existing metering systems. We can see why the data is important for that, though. Needing good quality data to develop those models is really critical. And usability of these tools are important. So that was one of the things we're keeping in mind as we're working on this, is continuously getting feedback from Scott and from the installation folks, to make sure that what we're developing is easy to understand, easy to use, because we want to make sure that we're not just developing shelfware, and that we're developing something that installations could actually use. So benefits to the DoD. And one of the things we're keeping in mind as we're working on this is that sort of cost-effective metering cycles, I've started calling it, where we can use these analytics to predict water use in some locations, prioritize metering, get more data, and continue updating these models till we get to the point where we have a really good understanding of water use at the installation, and we can do that in a cost-effective way. So really setting up that data-driven prioritization of metering and utilizing the data that's already out there to make informed decisions. And clearly we've seen especially for the region that we're looking at in Southern California, understanding water use and for resilience is really critical, especially for drought-prone regions, to be able to plan for the future and plan for mission sustainment. So these are some of the links we pulled those images from in the slide. So just wanted to share those, and happy to answer any questions there are now. And here's Scott and I's contact information. If there are any questions or any more detailed questions, we can answer after this. But thank you all for your attention. Thank you, ESTCP, for hosting the webinar, and happy to answer any questions there are right now.
Great. Thank you both. And to our audience, please type in questions for Connor or Scott using the Q&A box on the Zoom screen. And the first question we have for you, Connor, is from the Naval Support Activity Monterey. And the question is about providing training. Would you provide any training to installation managers if they start using this type of modeling?
I think the training would be around the tool that we are developing. So specifically the geospatial tool utilizing, we're using Esri Insights for that. So the analytic results are built into that. The analytics themselves are sort of out there for all to use. These are, based on academic studies. So we would certainly, give a training around the geospatial tool that would be developed for a specific installation. But in terms of and provide background on how those estimates are developed. So yeah, that could be part of a geospatial tool training.
Okay, good to know. Thank you. Next, machine learning models in general can miss predictions for extreme events because those extreme events may not be in the training data historically. So have you considered this, and have you thought of ways to overcome this?
Yeah, that's a really good point. I think for our purposes here, we see those big misses as sort of showing where anomalies exist. So if there are things like major water main break or high level of overuse, we would note that, or we would say, use the data to say, hey, there's a big anomaly here. We quote missed with the model, but what else is going on? What could explain that? So that's really how we're viewing the big misses in the model right now, especially in the model where we're comfortable with the results, is to use as, not just prediction, but a way to track and investigate anomalies in water use.
Okay, great. Thank you. This next question, I think, is more for Scott. So Scott, we'll start with you. Can these approaches that were discussed in this presentation be scaled from a single installation, like considered here, to being implemented as a broader or enterprise level approach?
Yeah, so I think one of the big reasons that I have become involved with this and wanted to push this forward is simply for that reason, is how do we consistently apply the things we're talking about across all installations and set like a core set of analytical points that will help us prioritize where we need to put specific to. I mentioned the word funding and resources multiple times, and I can't articulate enough how competitive it is within the facilities environment to obtain what are very limited resources. And to advocate for things such as metering is challenging because when you're sitting in front of a money person, you need to articulate to them, what's the benefit. Oftentimes it's seen in, is there a return on investment involved? Water is a relatively inexpensive commodity. What has popped up recently, however, and Connor touched upon it, is now you're looking at a geographic region in the United States that's becoming challenged in terms of now availability of water. And the Marine Corps has a big presence in that area. So we definitely want to get an understanding of not only cost, but operational impacts. And if we can look at those analytical factors across multiple installations. That just makes it easier for us to prioritize where to put our resources.
Got it. Understood. Thank you very much, Scott. And following on that, Connor, more of a question for you. I think you talked about the differences between this installation and potentially others, and that the results and approach from this installation might apply to arid installations in the Southwest. What differences might there be geographically between installations that would need to be considered?
Yeah, it's a great question. I think one of the things that comes to mind is just kind of patterns of water use. I mean, not even thinking geographically, but just what types of facilities are on different installations, how are water use patterns different, different irrigation needs, things like that. I think you just thinking about those things, those are kind of transferability questions, which we're really excited to try to dig into. You know, you would assume that there'd be similar maybe seasonal patterns based on certain regions, and there might be that strong temperature correlation within similar regions. So I think those are some of the things that we're keeping in mind and really looking forward to trying to dive into in a future phase of this.
Okay, very good. Thanks. Okay, at this time, we would like to bring Hunter back on the line, and we have just a couple of questions for all of our speakers today. The first topic for everyone is about AI. What do you see as the role of AI and other advanced analytic approaches like machine learning towards improving water monitoring technologies? So Hunter, we'll start with you.
Okay. Yeah, I believe it'll have a large role moving forward, especially if you consider how much the field has grown over the last few years. So it's definitely going to be useful for, improving or adding new capabilities to how we maybe handle our data analysis, or how we, look at existing technologies. So yeah, I think overall, just a big role.
Okay, great. And Connor, you would answer the question, please.
Sure. Yeah, I agree. I think with machine learning and AI, we're able to get a lot more out of the data that we have than maybe previously we didn't have the opportunity to do that. I think, both of the examples that we saw today are looking at really potable water distribution, but there's a whole world of opportunity even looking at wastewater, stormwater networks, climate. I mean, I think just in terms of developing analytics or assessing data, I think we're really just, as a water industry, really just scratching the surface. So I think there'll be a lot more work focused on AI and ML in water in the coming years.
Okay, great. It's really exciting field. And one last question for you both, starting with Hunter. Would you each describe the next steps in your work? If there's some very short-term next steps, but also just a little bit longer term follow-on work for the approaches you described. Hunter?
Yeah, so direct next steps would probably be, looking towards implementing and transitioning this technology at other installations, maybe branching outside of just the Southwest region and, other locations in the US or maybe overseas as well.
Okay.
Yeah.
Great. Thanks, Hunter. And Connor, next steps, short and long term.
Yeah, so short term for the first portion of this project are really to make sure we're comfortable with the approaches that we're using, and that the Marine Corps is comfortable with the approaches that we're using in terms of prediction. So working with Scott and his team on both understanding those predictions and making sure that we develop a tool that integrates that data in a good way that's usable for installation managers. That's kind of near term, and then long term, we're figuring out how best to scale this into a more instead of a prototype approach, really an enterprise type approach that we can transfer to other installations, probably focused on the Southwest US, but not limited to that at all. So that's where I see it going for both near term and kind of longer term.
Great. Thank you. And at this point, we'd like to thank all of the speakers today for the presentations and for answering all of the questions. And for this webinar series, we'd like to let the audience know that our next webinar is on Thursday, March 21st, and this one will feature DoD-funded research efforts to develop and improve tools to support climate management planning. Please visit the Startup in ESTCP webinar webpage. You can register there for this and other webinars through the end of 2024. And as we conclude, I would like to remind you both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you want to refer to them in the future. And we would appreciate it if you could please take a moment to complete the survey that should pop up on your screen at this time. And this concludes today's webinar. Thank you.